Okay, so now we're going to talk about quinoline and isoquinoline syntheses. These have been in the news a bit because they are part of those drugs, chloroquine and hydroxyquine, that you probably heard about as possible cures for COVID. And they also lead us into another discussion that we had earlier, remember, about having doses where the potency was very high, and also the lethal dose was very high. So remember we had that discussion about, oh, if somebody a drug's really powerful at 1 microgram and you can make a pill that is 1 microgram, that's great. But if it's lethal at 2 micrograms, you could forget to take your pill, take another one, and die, right? And so that's actually what happens. Can happen with some of these drugs that have been said to be good for COVID. It is that 1 gram is good for you and 2 grams will kill you. So this is something that's coming up in the news right now. Okay, so now talking a bit about these the molecules that go into these drugs, and that is these quinoline and isoquinoline drugs. So they're important antibiotics, painkillers, and dopaminergic drugs. So here are some antimalarials. So this is that drug that's been in the news, chloroquine. That is an old school antimalarial. So what I mean by old school is that most malaria, which is a parasite that lives in mosquitoes and gets transferred to humans, most malaria parasites are now resistant to chloroquine. So it was a big deal when it came out, and people started taking it, say, in the 50s. But now, in a lot of places in the world, they're resistant. For example, places like Thailand and stuff are places where the mosquitoes are resistant. Some places in Africa, I think you can still take this. There's also, so these are to kill parasites, and these anti-malarial drugs are parasites are more like us. They're eukaryotes. Their nucleus has an envelope, so they're much more sophisticated than bacteria. And honestly, once you take the jump from bacteria to eukaryotes, it becomes much harder to differentiate between eukaryotes when you go to kill something. So what I mean here is when you go to treat somebody for a parasitic infection, it's really challenging because the parasite, which is a eukaryote, is going to be killed by most of the same things that kill a person. So most of the things that kill a yeast cell will kill a human cell. And so that becomes very challenging from a medicinal chemistry standpoint. What we also use these for are antibiotics. So remember, antibiotics, that's an antibacterial. And so these are a lot of really popular antibacterials, right? This is ciprofloxacin, so that's Cipro. So that's one of a really good antibiotic right now. I'm sure bacteria are working on left and right, creating new resistant strains to it. But that is the antibiotic, an excellent antibiotic. And so these kill not only eukaryotic cells, but also prokaryotic cells like bacteria. There are also some really important anti-tumor chemotherapeutics. So these are camptothecin, is a really important chemotherapy drug, and also irinotecan, and we'll talk again more about this when we're in our chemotherapy unit. But these have, again, this quinoline unit, and they have this quinoline unit here. And so what I would say is clearly this is a privileged structure, right? It does a lot of different things. It can treat a lot of different, a wide variety of diseases. So one of the ways to make quinolines is using the Combs-Quinoline synthesis. And so this is a really well-known reaction. And one of the ways to do it typically for that acid there is you want to have a concentrated inorganic acid. So you want to have like a mineral acid, something like sulfuric or HCl. You can use PTSA, para-toluene, sulfonic acid. Also for the dione there, that diketone product, you can use unsymmetrical diketones and you can get, you can get different products. And it can be hard to get particular distributions of the R groups, different ways that you can do with the Combs-Quinoline synthesis. So the mechanism of the Combs-Quinoline synthesis, so I'm going to want you to go to video 3 here, and I'll go through the mechanism. Another way to synthesize some of these quinolines is using the Conrad-Limpach and Knorr reactions. So if it's the, you're using the same reactants here. So if you're using this reactant with acid, it's a Knorr reaction. With heat, it's a Conrad-Limpach reaction. And notice that you get a different substitution pattern. Notice that the R group's in the same place here, but the R group's over here now with the Knorr reaction versus here, and you've also got the OH group. And so these compounds are known as quinolines. And what this is that this is, with acid, this is the kinetic product, and with heat, this is the thermodynamic product. So this is technically the more stable product thermodynamically, but this is the one that's faster to make kinetically. So the faster to make product is not the most stable product. And when that's the case, we can split the two products apart. So we can make both products using different reaction conditions. So that's kinetic versus thermodynamic products. So here, again, we're using Conrad-Limpach. So again, this is using heat. And we said before that this is the thermodynamic product. So now we use heat to create this hydroxyquinoline. So this is like the 4-quinolone, just been oxidized, so it's aromatic. Or sorry, not oxidized. Sorry, this is the aromatic product, right? It's you can imagine this is a tautomer of this guy could tautomerize to this, right? The H group that was here is now over here, so it's a tautomer. And what you can do is you can use phosphorus oxychloride. You can convert this alcohol into a chloride. And then you can derivatize off of this chloride to create chloroquine. So remember that chloroquine had those basic groups coming off here, the basic nitrogens. We can also use Conrad-Limpach to make mefloquine. So this is another common antimalarial. So notice here that they're using our pyridine. We're using a lithiated pyridine species to create a substituted pyridine. So taking us right back to that previous slide. Notice here we have again the conversion of an alcohol to a halogen using a phosphorus oxyhalide. And here we are doing a lithium halogen exchange with N-butene and CO2. So you just treat this first with N-butene to make the lithium salt, the lithium organolithium species, and then you add in CO2 gas or some kind of CO2 source here. And after that, you're going to get the carboxylic acid, which then you can react with your lithiated pyridine species. The Friedlander synthesis, the main note about this is that you don't get a mixture of products with meta-substituted anilines. So the meta substitution here on this, this is an aniline, right? RNH, the aryl NH2 is known as an aniline. So if you have this meta substitution, you're not going to get a mixture of products. So that can be helpful when you're doing when you have substitutions on the aniline side. Before we're having substitutions on essentially the pyridine ring side that we were talking about. Another common synthesis of quinolines. These are really common. That's the Skraup or the Doebner-von Miller reaction. So the Skraup reaction, notice we're using that triol here, and we have acid and an oxidation step to get the quinoline. Here we have an alpha beta unsaturated carbonyl, and we're getting a quinoline. So this is a way to get our groups here. And again, both of them go through an acid and a oxidation step. Isoquinolines. Okay, so isoquinolines are, if we look at the quinoline, the nitrogen was here. Isoquinolines, the nitrogen's going to be here relative to the aryl ring. So quinoline versus isoquinoline. The most famous reaction really to make this is going to be the Bischler-Napieralski reaction. And where the substitution, so you can have a lot of different substitutions here. Where this R group ends up is the carbon on this ring that has more electron density. The R group's going to end up adjacent to the carbon that, or on the carbon that's going to have the more electron density. So for the mechanism, go to the mechanism slide not mechanism slide, the video for the Bischler. So I think that'd be video 4 by now. So using this, we can make isoquinolines. There are a number of different ways. Another example of a synthesis like this is the Pictet-Spengler reaction. So here what we're doing is we're forming that imine first, and then the ring is going to attack, this mechanism's bad. The ring is, this arrow is going the wrong place. The arrow should go here. Arrow should go here. People. So here's an example of this isoquinoline synthesis. Notice in this case that we're doing that oxidation at that last step to get to the isoquinoline. So this is papaverine. That's a natural product that's from the opium poppy. It can also be found in other papaver species, various different poppies, and so this is used as a vasodilator to improve circulation. The Pictet-Gams reaction is basically a dehydration reaction. P2O5 is going to want to pull this oxygen off because phosphorus loves oxygen, like we were talking about before, and so this is a dehydration to get to the isoquinolines. So the mechanism is pretty long. Notice again we have that same, what's happening here in the Pictet-Gams reaction is the same kind of, in this step is analogous to the Pictet-Spengler reaction. So you have the aryl ring attacking the imine there. And the Pomerantz-Frisch reaction, where this is the synthetic equivalent of an aldehyde here. And so with acid and heat in C2, you'd be generating that aldehyde. So what you want is an electron donating group para to the site of ring closure there. So unsubstituted quinolines and isoquinolines are poisons, and that's one of the things that we actually use them for. We substitute them, and then their antimalarials can be really safe. And by really safe, I mean you can take a gram of them. Of course, 2 grams you can die. The quinolines, so this can be stuff like ciprofloxacin. They can have adverse reactions. They're really good, but they have drug-drug reactions.